Hello everyone, welcome to today's lecture. Today I'm going to talk about operating systems. Let's go a little bit back in the history of computers and think about the initial computers. In those old computers, in 1940s and 50s, the computer was only running a single program at a time. These programs were written into punch cards, and then the programmer, for example, had to carry those punch cards or magnetic tapes on which the program was written, and then they had to hand the program to a human operator. And then that human operator that operated the computer would feed the program to the computer, and then the computer would process and execute the instructions written in the program and then produce some result, hopefully. There were many cases that, of course, the program had the errors and bugs and they had to be fixed and so on, but we don't consider them in this lecture. Here we are going to talk about programs that are working usually as expected. Computers were slow at those times, and program execution would take a lot of time, being several hours or days or even weeks. But as we had seen in the lecture about history of the computers, we saw that Moore expected that the computers would become faster and faster exponentially, and this was based on a observation in the history before his time, that the technology had evolved in exponential. And this trend actually continued. The computers became faster because the electronical parts developed and they became transistors, and then the transistors got smaller and smaller during time, and when they got smaller, so they were placed closer together on the chips inside the computer, and then because they were closer, so the data inside the computer would flow faster. So then this made that the computers became faster during time. This was one of the reasons. So as computers became faster, human operators were too slow compared to the computers. And usually it was that the operation time would take much longer than the program execution because computers had become so fast. Here in this picture, it is interesting. You see the biggest program written in punch cards. That program belonged to the US military and was written on over 62,000 punch cards, which only was equivalent to 4 or 5 megabytes in size. So you see how tricky this would be to just feed this program correctly to the computer. So it would take a lot of time, but the execution might not take that long. So the computers needed a way to operate themselves. Human operators were not good enough anymore. So the computers needed themselves to operate. And this was the reason why operating systems were born. So the first operating systems appeared in 1950s. Here you see the first operating system for personal computers. So every computer needs an operating system. For example, mainframes and servers and personal computers, and even our cell phones today need operating systems. So the operating systems then replaced the manual task of loading programs by hand. So an operating system is simply a program. Some programmers write the program for the operating systems, and these programs that are operating systems have special privileges on a computer hardware, meaning that they have access to all hardware devices. They have direct access, as opposed to other programs that we write. For example, you had seen in the assembly program that each time we had to print something or get an input from the user, which is essentially an input or output operation, then we couldn't directly access the input or output device. We had to use system calls. So with system calls, we are actually asking the operating system to do that operation for us because we don't have access to the hardware devices. We are not allowed to do that, but operating system has such access. This is to protect the computer from malicious behavior. So operating systems have special privileges, and with that, they can manage and run other programs. So when you turn off your computer, first a small program called BIOS starts, and that program starts your operating system. And then this is the operating system that launches and runs other programs. So this is the main program in your computer. So we will, in the rest of this lecture, talk about different functionalities of operating systems, being batch processing, process management, resource allocation, scheduling, multitasking, memory management. We will see why they were needed and how operating systems evolved during time to have these functionalities. The first operating system didn't have most of these functionalities. They started with, which we will see, with batch processing. But then later on, operating systems evolved and became richer and richer and are offering more functionality. So the first thing that was expected from an operating system would be to execute several programs one after another. Because when you have a computer, imagine you would execute several programs on it, and you wouldn't like to feed the program each time separately by hand. So you would like to combine your programs and feed all of them to the computer, and you would like the operating system to take care of their execution and execute the programs one after another one. So this was the very basic functionality that the first operating systems offered. So then this removes the need for human operators. So here, imagine you would first feed all the programs to the computer, and then you then give the rest of the control to the operating system, and the operating system would take care of the execution. Then the computer would generate results for each program separately. This is called batch processing. So you give a batch or a cluster of programs to the computer, and the operating system takes care of it. So as the computers continued evolving, they became cheaper and faster and more widespread, and they popped up all over the world. And people, especially programmers, started programming those computers, and they liked to share their programs, to share their software they have written. For example, imagine they had written a game or some application software, and they would like others to use it for example, to sell it, their software and so on. There was a problem at that time. So different computers existed in the market. All different computers had different architecture. So their hardware was different. And the programs that were written at all times depended very much on the hardware of the computer. So they were very specific to one computer that they were written for. And not only the computer, but also they depended on different devices that were connected to the computer, for example, to the printer and the display and things like that. So this would, first of all, make programming very difficult because the programmer would consider all the different cases of different computers that are in the market, and they also had difficulty to test them because a programmer would not have access to all the computers and all devices that would come with the computer. So the programs became faulty, and in many cases the error would happen and the program could not be executed. Imagine, for example, a programmer would write a program for a special CPU and a special printer, but If another one that had the same CPU but a different printer might not be able to execute that program. So there was a need for getting away from all the details with different hardware devices. These hardware devices that are connected to the computer are called peripherals. So operating systems then enriched to be intermediaries between the software programs and hardware peripherals. So they provided software abstractions, which were called device drivers. Device drivers are simply programs that operate a particular type of device that is attached to a computer. For example, any printer or headset that you connect to your computer has its own device driver, and operating systems used these device drivers, and some device drivers that are embedded inside operating systems. So these drivers hide many details from the programmers about the hardware, about the architecture of those devices. So they take care of the details themselves, but then the programming becomes easier because, for example, imagine you want to print something in the printer or write it on the display, then you don't need to care about all the details. How should this bit and that bit be, etc., etc. You just would issue a print statement, and then the device driver translates this somehow and takes into account all the details about that specific hardware device. So for example, whenever you write print operation in Python, you don't care about what is the details of your display and how it will, because there is a device driver which is taking care of all those details, and operating system is actually using that device driver whenever it wants to print something on the screen. So let's again take a look at history. So by the end of 1950s, computers got so fast, and because they were using electronical devices, they were using transistors, but the printers and so on were mechanical. All input-output devices, which we write for short I/O devices, were mechanical and they were slow. For example, punch card readers and printers were slow. Then what happened was that the processor times were wasted. What does this sentence mean? So imagine you have a CPU, you have a processor, and because this device is expensive and it is a resource for you, you want to keep it as busy as possible. You don't want to leave it idle. When you have work to do, when you have programs to be executed, you want to utilize your CPU as much as possible. But there were programs that didn't need only CPU. They needed to, for example, read something from input device or write something to some output device. And those devices were very slow. So then the program had to wait, and CPU couldn't execute anything else because that program had not finished. So then they would be idle and waste the time. So in this case, we say the CPU time or process time was wasted. In 1962, actually, the first operating system was introduced that did multitasking. This is a very great breakthrough, and there is a lot of research even today about how to achieve multitasking in a better way. So multitasking, I will explain in several slides, but before we go there, let's first define some terms. So we want to define a program and a process and see what are their differences. And I will show you an example as well. So a program, as we have seen so far in the lectures about Python programming and assembly programming, is a collection of instructions. It is a passive entity, which is just stored in secondary memory on your computer. Secondary memory, I will explain in the next lecture, is all the memory that is attached to a computer, like hard drives or CDs, DVDs, USB flash, etc. So a memory is just a piece of text or binary, sorry, a program is just a piece of text or binary instructions that are stored somewhere. They are not executing, just they are stored. But as opposed to that, we have the process, which is an instance of a program, which is loaded into memory. In this case, it is primary memory. We will talk about it later. And they are executing or waiting. So whenever you start executing your program, that entity that is running is called a process. We don't call it a program anymore. So imagine or think about the previous lecture where we were talking about assembly programming. So first we would write our assembly program in a file. This is a program, but as soon as we clicked on the run button, then we would start a process, and we saw that memory was allocated to that, registers would reset and serve to that process, and that its text, I mean the program was loaded in a special place in memory, and then it would start and run, and it had a program counter, or PC for short, that would show in which line we are executing and so on. So that entity is called the process. I will show you an example now. So let me open idle to write a very small Python program. So here I have a very small Python program, which just consists of an infinite loop. I have a while loop for which the condition is true, meaning that the body of this while loop will execute all the time. There is no end to that. And it will just print this string for me when it is executed. So this is the program. This is just stored on my hard drive, and it doesn't do anything on its own. It needs to be executed. And as soon as I execute that, we will see that what is the difference. So before we go there, I want to show you the processes in my computer. So on Windows, you can use the short keys Control, Alt, and Delete to see the processes that are currently running. So if I press them, then I choose Task Manager, then I can see here processes. So all these processes are running on my computer. So all the programs basically that are running are basically one or several processes. And then, so take a look at this list. So we don't have any execution of Python code yet. So now I want to run it. This is my program. I double click on it. This is an infinite loop, and it will continue forever. This is terrible, but I just wanted to make sure that it takes a lot of time so that we see the process here. So you see this process was added. And this process, we can see how much of the resources it is using. So it is using this much of the CPU on the computer and this much of the memory, and it shows also other resources. So all the CPU, memory, the network are all the resources. They are called the resources in the computer. And so for my program, which was passive and stored on hard drive, now I have an active entity, which is the process that is running it. And now if I close this window, this process will be killed. Actually, this is the operating system that removes the process now. So I click here, and you see that this process disappeared. So this is the difference between a program and a process. So a process is an active entity and needs resources such as CPU, memory, input-output devices, etc., to execute. And OSs have another functionality which is very important. It is called scheduling. Scheduling is the action of assigning resources to the processes. And the scheduling activity is carried out by a process inside the operating system, which is called scheduler. So all operating systems today come with scheduler, and their schedulers might differ in how they schedule processes, but they have this goal of giving the resources to the processes, and we will see, they say when a process can run and when it cannot. So there are different approaches when it comes to scheduling. Imagine you have several processes that are all willing to execute on your computer. One approach, the simplest that one can think, is just to let the processes to run as long as they want, and then the next process continues if the previous process had finished execution, or in case the first process decided itself that it wants to stop for a while. Otherwise, so for example, you see here process 1 is running, and these blocks here show the amount of time it is consuming. So it is running for some time, and then it is itself that decides to release the resources, for example, release all the CPU and memory that it had occupied. Then the scheduler would pick process 2, for example, in this case, and let it run. And then process 2 here just releases the resources. Maybe it decides that it doesn't need them for now, something like that. Then you see here process 1 is going to run for a substantially long time, and no one can interrupt it. So it will run as long as it wants, and then the other processes have to wait. So this has clear drawbacks. Imagine you have the tiny processes that have to wait a long time for very big processes to finish. And this is not fair. Some processes may never get the chance to execute because there are other processes just executing before them, which are very long. So this approach, which is called non-preemptive scheduling, might not be desirable in many systems. There is a counterpart to that, which is called preemptive scheduling, in which the approach is different. So here, the processes are given equal time slots. So the time slots of the time of a CPU is divided into small chunks, maybe a fraction of a second only, and processes can only run during that time. And when the time is over, then the process cannot continue. So when this time is up here, then another process has to run. But it can be that the execution of a process is shorter than the amount of time that is allocated to that. So then that process will finish, and then another process can continue as well in that case. Otherwise, this process will be interrupted. We were going to use the word interrupt several times during this lecture. This is very important. So interrupt is like you stop some process for some important reason. For example, each time you press a key on your keyboard, there is an interrupt issued by the operating system to store the result of the key that you have pressed somewhere in memory and take the corresponding action. For example, maybe you have pressed the power button, then it had to turn down your computer, or maybe you have pressed control or whatever keys on your computer that come with a special action. So then the operating system would interrupt any process, almost any process that is running, and take care of this pressed key, and then come back to that process. So this is some kind of interrupt. There are other interrupts. For example, in this case that we are dividing the time between processes, each time their time is up, they are interrupted. So this is called time interrupts. Then the control is somehow taken from that process and is given to another process. But what is important is that the state of that process needs to be stored so that later on you would come back to the same state as before and continue from there. Otherwise, you would just start a process from the beginning each time, which is not good, of course. So this is something the operating system takes care of it, that to store the state of a process and then the next time restore that and continue from there. So let's see an example. So imagine you want to print something, print on a screen on the display in Python. This would take a lot of time because even today, the input-output devices take much longer time to operate than the executions on CPU. So then, because CPUs are electronic and fast. So this process might be waiting for the display to do this job. So this doesn't need anymore to consume the time of CPU. So this process would be waiting just until this job of printing is done. And then in the meanwhile, another process would be able to use the CPU. And then whenever this printing is done, this process that wanted to print this statement would wake up and continue its work. So in this case, several processes can share the time on a CPU, and they can share actually other devices like I/O devices. This is called multitasking. So you are performing multiple tasks together to increase utilization of your whole system. So when we have multitasking, we need to take care of resource allocation. Actually, this is the job of operating system again. So if there was only one process, then there wasn't any problem with resource allocation. Resources are, as I said, like CPU, input-output devices, network devices, etc. So a process might need some of them or all of them as much as it wants. So the operating system needs to provide these resources for the processes as they need. So if there was only one process, then all the system would just be allocated to that process. But as we discussed, this is not preferable. We need to have multitasking to have better performance. It is inevitable. So then the process has to take care of the processes that are running. So because the operating system is the only program that has direct access on hardware devices, so processes will tell operating system or will request whenever they need something. And for that purpose, they use system calls. For example, we had seen how we use system calls to print things on the screen or to ask the user for some input. There are other system calls. The list of system calls is very long. For example, for even creating processes, you need to use different system calls. So processes use system calls to request for resources, and then if that kind of resource is free, the operating system can directly give access to that. So operating system needs to know what are the available systems, the available resources in the system. So this is called the resource pool. There is a pool of all the resources in the system. But if a resource is not available, so then before that, let's continue. Let's consider the case that the process terminates. So if a process terminates, then all the resources that were allocated to that will be deallocated, meaning that they will be freed. For example, if it was consuming memory, that memory will be free. Or if it was using the printer was allocated to that, then it will become free so that other processes will use that. So operating system will take care of it and know at each instance of time which resources are free, which are not. And whenever a process requests something, if that resource is not available, then the process will be moved to a list of blocked processes. So the operating system has to take care of this list and update it all the time to know which processes are waiting for which resources, and then later on when it sees that resources are available, it will remove that process and give it the resource it needs, and constantly do this kind of management. There is another thing that operating systems have to manage to achieve multitasking. It is called process management. So processes are active entities. During their lifetime, they go through different stages in their life. So, and this is the operating system that takes care of the processes and changes their state in time. So for example, as soon as a program needs to be executed, a new process is created. So each time you saw when I wanted to run the program, the Python program, then a process was created for that. So this is something the operating system does. And when a program is created, then it is moved to the set of ready processes. So operating system has to keep track of the set of ready processes, meaning that those processes that have the resources they want and they can execute, but they are not yet executing because at each time, just one process can run. Then from this queue, whenever it is the time for this process, so I said that at each time only one process is running, but we are talking about multitasking. So this should not be confused together. So at each instant of time in single processor systems, just one process is running, but this fraction of time is very small. So it feels like that when you have multitasking, it feels like that several processes are running together. But as long as you have just one CPU with one core, only one process can run. This is multitasking gives the illusion that several processes are running at the same time, but they are actually doing different things. So maybe some of them are waiting for hardware devices, one of them is running on CPU, and then they take turn very quickly. And this gives the illusion that they are running at the same time. And it actually is not just an illusion. It will utilize your computer in a much better way. So the new process is moved to the ready queue, and then the scheduler actually has the job of picking a process from ready queue and running it. So how this decision takes place actually depends on the algorithm that the scheduler will use, and we will discuss it in the coming slides. So then imagine this process is selected and it is moved to the running list. It is actually running. So then it will run and continue running until it is, for example, its time is up, or maybe it needs some input-output devices, or maybe some other interrupt will interrupt it. Then this will be, if it wants some I/O device which is not available yet, then this running process will move to another list, which is called the waiting list. In this list, there are all the processes that need some resource that is not available yet. As soon as that resource becomes available, the scheduler will move them to the ready list so that they are ready to be picked in a later time. So there is a difference between waiting list and ready list. In waiting list, there are those processes that need some resource which is not yet available. In the ready list, the resources that the process needs is available, but it's not just yet the turn for that process. So it's waiting its turn only. So then from the ready list, eventually the process again will continue to the running state, and then if it has finished execution at some point, it will terminate. So then a process comes once to this state and once to this terminated state, but it will several times move between these states. So whenever it is running, if its time is up, it will move here. If its resources that it wants are not there, it will move here, and then eventually to the ready list, and so on and so forth until it terminates. So all this is something which is taken care of by operating system, and it's a scheduler, and it is called process management. So as I said, the way how a scheduler selects a ready process to run depends on the algorithm which is used in the scheduler. Algorithm, if you remember, is a way to solve a problem, is a solution for a problem. The problem in this case is that you have a set of processes and you want to decide which one can run now. So the very basic solution that one can think of, and the initial schedulers did, and it is even used today in some schedulers, is to use the first come, first served approach, or FCFS for short. This is a very basic algorithm. It says that those processes that come first to the ready queue will be run first. So ready, as you see here, is a queue. In this case, we don't know how it is implemented. We have not yet gone to the details here, but in case of first come, first served schedulers, we know that it is a queue, and which each time a new process is created, it is added to the tail of the queue, for example, to here. And each time a process wants to be chosen to run, the first process will be chosen from the queue. And whenever a process is waiting and then its resource becomes available, it will be inserted into the front of the queue. So these orders are matters so that a queue is really a queue. It's like a queue that you would stand in everyday life. So in this case, the processes will just be treated equally, and they will be executed one after another based on the order in the queue. And it's the simplest and easiest scheduling algorithm, but this method is poor in performance because there might be some processes that are more important and they should run sooner, or maybe they're just very small, and if you put them at the end of the queue, they would just be delayed a long time. So this algorithm doesn't always work best. There is another algorithm called priority scheduling, in which case all processes in this system are given a priority, which is a number, for example, 1, 2, 3. And this priority can be assigned internally or externally. For example, the user might give the high or low priority to a process. And then each time a scheduler wants to pick a process from the ready list, it will pick the one that has the highest priority. And if there are several processes that have the same priority, then the first come, first serve approach will be used only among those that have the same priority. So multitasking is very much liked. It utilizes your computer in a very good way, but we have seen so far that some challenges, for example, the challenge of scheduling different processes, the challenge of managing processes during their lifetime, and the challenge of allocating resources to all the processes that are in the system. There is yet another challenge, which is called memory management. So each process that wants to run needs some amount of memory to load the code of the program, to load the data that it needs, and so on. So an easy way would be just give all the memory to a process that is running at the, and it is clear that this is not efficient, because then what would other processes do? They also need their own memory. One solution would be to just allocate to each process a block of memory, a chunk of memory, a limited amount of the memory. So in this case, different processes can have access to the memory, but still it comes with a problem. And the problem is that imagine some program starts running. In the beginning, it just starts with a chunk of memory and it is enough for that. But later on in its execution, it needs more memory. For example, it reads something from a big file and it needs to store it somewhere, so it needs more memory. Then this process can ask the operating system to allocate to it memory, but the problem is that maybe a chunk in another place of another part of the computer memory is assigned to that. So then the memory, which is in total assigned to a program, might be scattered through the memory. So imagine here we have two processes that have started, process A and process B. So the memory in a computer is built of bytes. So each byte, which has actually 8 bits, has an address in the memory. So all the bytes in the memory have their own specific address. The addresses can, for example, start from 0 and continue up as much as the memory size allows. So imagine the process A starts first and it takes the first 1,000 bytes in the computer memory. And then process B starts and it takes the next 1,000 bytes. But it can be that process A realizes later on that it needs more memory. So it asks the operating system to assign to it more memory and it will be assigned, for example, another 1,000 bytes, but you see here, in another part of the memory. So these blue parts are not besides each other. So this will make some difficulties for the programmer, because the programmers then need to take care of which addresses are exactly allocated to some process that is running. But it is not preferable, of course. The programmers don't know what are the exact addresses. They can use some programming instructions to read the memory address, but this is very difficult to handle. So the solution is that give this job to operating system. And operating systems in this way manage the memory. So they, first of all, allocate memory whenever processes need, and there is enough memory for them to be allocated to them. And also they do something else, which is called virtualizing memory. So this means that they will hide some of the details from the programs. So let's see in an example. So first we go through the specifics of virtual memory. So in virtual memory, the programs assume that their memory starts at address 0, although we saw in case of process B, for example, that it had not started at address 0, but the OS lets them to make this assumption to make their work easier. So they assume that they start at address 0. So this makes the job of programming very simple and consistent. And the actual physical address is taken care of by the operating system. So let's see an example here. So we have the two processes A and B that we had seen earlier. So we said in virtual memory, each process thinks that it has a memory that starts at address 0. And actually, they think that the amount of memory which is allocated to them is not scattered. They think that the memory is just a single block. So process A in this case would think that addresses 0 to 999 to actually 0 to 1999 is assigned to that. So although these two parts in the physical memory are not beside each other, but process A makes this assumption because the operating systems allow them. So this is called virtualization. So it means that there are some details that the processes and programs do not need to care about. And process B also thinks that it starts at address 0, although it is not really the case. It started at address 1000. It might seem problematic, but it is actually not, because why do processes need memory addresses? They need them to store something in the memory and read something for the memory. But this reading and writing has to go through our operating system, because we have discussed that operating system is the only program that has direct access to memory and CPU and so on. So because the operating system is on the way and it knows that these assumptions were made by the processes, it can take care of the actual addresses, which are called physical memory addresses, by itself. So for example, in this case, imagine program B requests some data at virtual memory address 67. So because it sees this place, it sees only this virtual addresses. So then the operating system will actually translate it to its actual physical address, which is 1067, because the beginning address in case of B was not 0, it was actually 1000. And in case of process B, imagine that it wants to access memory location 1000. So this is the virtual address that it wants to access, but the operating system knows all the details about the allocation of memory to A and knows that whenever A wants address 1000, it is actually corresponding to the address 2000 in the physical memory. Then operating system will go to that physical address and fetch the data that, for example, process A wants. So then the process A doesn't need to know exactly what different blocks of memory are assigned to that, because there might be several scattered chunks, and computing the actual physical address might be very difficult. And this burden is actually taken from the programmers, which makes programming very easy. So let's review the benefits of virtual memory. So first of all, it allows that memory be allocated dynamically. Dynamic is as opposed to static. So in a static, you would decide in the beginning how much memory you would give a process, which is not a very good approach, because some processes might need much less, so the memory is wasted, or some processes might need more, so then they cannot execute and they crash. But when you have dynamic memory allocation, the program sizes and their memory requirements can be flexible, which is very good. And another benefit of virtual memory is, as we discussed, that the allocated memory appears to be continuous to the program, not scattered blocks, which of course simplifies programming. And the virtual memory gives the flexibility to the operating system in running multiple programs simultaneously. Otherwise, if we didn't have virtual memory, then either the programming would become too difficult, or we had to simplify it by fixing the memory assigned to each process, which would limit multitasking a lot, because then maybe we needed to give a big chunk of memory to each process, then fewer processes would be able to run. And it has actually other benefits. For example, programs are isolated from one another, because no program can have access to the other program's memory locations. So this is something the operating system doesn't allow, and they don't even know the physical addresses of other programs. So then they can only access their own addresses. So in this, with this functionality, if there are buggy programs that they trash memory, they can only trash their own memory. They will not be allowed by the operating system to trash other processes memory. So this is called memory protection. So with virtual memory comes also memory protection, which is a very important functionality of the operating system. And memory protection can also protect your computer whenever there are malicious software like viruses that want to trash the memory. Then operating systems have some degree of control to not let the malicious processes to do anything they desire. So let's continue again in the history. By 1970s, computers were continuing to become faster and cheaper. So different universities and organizations would buy computers and let several students or employees work the same computer all at the same time. So they would give several users simultaneous interactive access to just one computer. How would this be possible? This was actually possible by some devices that are called terminals, as you see in this picture. This is called a terminal. A terminal is a keyboard and a screen that connects to a big and powerful computer. So a terminal doesn't have its own processing capabilities. It just transfers the input from the user to the computer, and then the computer will take care of the processing, and then the terminal again would transfer the outputs from that big and powerful computer, which is shared to the user. So several users, for example, up to 50 users would be even able to run at the same time. There is a challenge when you have multiple users, and it is that you don't want to let one single user to consume all the resources of the computer. You want all the users to share them. And this was achieved using time sharing, meaning that each user is given a tiny amount of time in which it can use all the CPU and resources of the computer, but this time is very short, maybe shorter than a second. It's just a fraction of a second, and then the control is given to the next user and next user and next user. So because the computer is very powerful, all these users will actually have the feeling that they are the only one that is using the computer, because even in that fraction of the second that is assigned each time to them, many processing can be done, so then they can continue their work and they would not feel a lag. Even now, these terminals are used in many universities. Maybe you have seen them in the computer labs of the universities that you have studied, that there are terminals and they are connected to some servers that we don't see, but they are those powerful computers that take care of executing the work of all the users. So during the history of computers, there have been many different operating systems. We will hereby introduce two which are very famous. So one is called the Unix operating systems, that they were introduced first in 1971. And they are a series of operating systems that have some common criteria. So in those, the operating system is separated in two parts. The first part is called kernel, which has the core functionality of the operating system, being multitasking, memory management, dealing with input-output devices, etc. And then besides that, there is a wide area of useful tools, other programs that are not part of the kernel, but are very much useful for the operating system. So the kernel is very important and is tried to be as small as and as simple as possible. In Unix system, there is another criteria which is common, and it is that the kernel, if it crashes, there is no recovery. So this makes, so then whenever a kernel crashes, you see a kernel panic message. This is in a Unix system. Unix systems are like, for example, Linux, Ubuntu, Fedora, etc. You might have experience running them. So kernel crashes when there are failures and it doesn't recover that. So because it doesn't need to recover, it makes it very easy to program, and it makes it able to uh, run on diverse hardware devices, and it becomes so cheap. Before these kernels and Unix systems were introduced, some other operating systems were introduced which were having error recovery procedures that were very much difficult to implement, and they needed a lot of engineering effort. So those operating systems became very expensive, so impractical. But Unix systems were the opposite, and they are open source nowadays. Different developers all over the world participate in developing them, and the kernel is easy and uh, small. So now let's continue a little bit in the history of computers. So in 1980s, computer prices had fallen so much, and the computers have become so small so that people could afford to have personal computers, or PCs for short. And these computers were simpler than mainframe computers or servers that were used at universities, organizations, etc. And because their users were usually not experts, they needed to have simple operating systems. So for this purpose, Microsoft introduced is MS-DOS operating system for personal computers. Its first version was only 160 kilobytes, and it could store on a floppy disk. And in the first versions, the operating system didn't have multitasking and memory protection functionalities. Even in the later versions, there wasn't any strong memory protection. So programs could crash the whole system if they crashed so badly. And then this blue screen of death that you see here would appear, and there wasn't any choice for the users to turn off and turn on your system, but it made them easy and affordable. So now our devices that we are using have modern operating systems, and they are usually run by only a single user, but operating systems have still multitasking, time sharing, virtual memory, and protected memory, because although we are just one user, we would like to run several programs, which brings up several processes to run on the system. For example, at the same time, we might be browsing the web, listening to music, editing photos, etc. All these need their own processes. Personal computers are not the only computers that we work with on a daily basis. We have talked so far in this lecture mainly about the operating systems on personal computers, and they also share a lot of common criteria with operating systems on servers and so on. But we have not talked about embedded systems that we use every day. Embedded systems are actually small computers that are embedded or built inside different devices that we use. For example, they exist in our cars, in many home appliances, etc. These kind of systems are do a specific task as opposed to the computers that do many sort of things. So embedded systems are told to be special purpose as opposed to PCs that are called general purpose. So because they have a specific task and they have a small processing unit usually, they are a simpler system basically. So some of them are so simple and they have such a limited memory that they don't have any operating system at all. But there are other ones that have sufficient memory and their processor is strong enough so that they have their own operating system. An operating system in these cases is called embedded operating system, which is a lightweight version of an operating system. Thank you very much for your attention. Please don't hesitate to ask your questions via email or for you, etc.